Thank you very much, Juan. Miguel, I don't know we are good until 2. And 3, we will have coffee or good. Okay, so we have 7 minutes for questions. Eva.
Thank you very much for the presentation. Could you please go to slide 28? Oh, maybe it's one before that. It's a photo of your model monopiles, I think.
Here.
When they were installed in the center.
This one?
No, the monopile. When they were installed in the model.
Ah, okay. Here.
Yes, that's it. So, have you facilitated an interface? I suppose the monopile, the material is aluminum, or right? Have you taken into account an interface for the monopiles? And if yes,
yes. Thank you. Yeah, because in the centrifuge we need we instrument strain gauge, then we put epoxy to protect the strain gauge. So we will have a different kind of interface between the soil and the prototype or aluminum pipe. But for this epoxy, we did some interface test before. The friction angle is different from the aluminum, but it's quite close. And also for the lateral response of the monopile, we also did some numerical simulations. The influence of the interface roughness in that range, even a very big change doesn't really affect that much the lateral response. But I guess if it's vertical loaded pipe, it becomes more important. Yeah.
And those were also hammered in, or were they wished in place?
Yeah, for the test at the terrace, we do everything in the wish in place because we, of course, first we don't have a hammer at the terrace, but more importantly, we want to develop a numerical model to validate the centrifuge test, and that's a little bit better to have better control of the soil if we do it by wish in place. So if it's hammering becomes a little bit complicated, then that's the next step. Yeah, for the numerical to validate. Yeah.
Okay, and there was it was further along in the slides. You don't have to go there, but you mentioned something between simulating drained and undrained conditions in the centrifuge experiment, and you were using water.
Yeah.
Water for saturation fluid and viscous fluid. Could you please explain this a little bit better?
Yes.
Because
So.
Yes. How do you facilitate the undrained conditions?
Yeah. So because we use the viscous fluid to decrease the dissipation speed to try to mimic the offshore wind turbine, try to capture what's really happening to the drainage condition. And before doing that, we kind of want to know, okay, if the difference of fluid itself, for example, if we use viscous fluid instead of water, will affect the response. And what we control here is basically we load the pile very, very slow to make sure it's fully drained condition. And then it shouldn't be matter what kind of fluid you use. And then that's the results we have. Like you can see here, they are really close. And there is some difference because of the rate density, but they are really close, which means the fluid, like the viscous fluid itself, won't change the mechanical behavior of the sand. Then following that, we go to the cyclic, then we study the drainage condition. Yeah.
The viscous fluid is of the proper G level, right? So it's at 100 CP.
Yeah, all the tests were performed at 100 G, but the viscosity is 100 times larger than the water.
Right. And then for the cyclic part?
For the cyclic part is still same 100 times viscosity, and we did displacement controlled cyclic at a different frequency. And then you can see because of the viscosity or because of the drainage condition between water and viscosity, and viscous fluid, you can see the response of the pore pressure. On the left, it's almost fully drained. You don't observe any variation of the pore pressure.
Both drained.
On the right, I agree. So on the right, there is a little bit undrained because we have this oscillation pore pressure, but very, very minimum. That's actually good because we want to kind of justify our judgment at the beginning. We think it's fully fully drained, or the monopile is more controlled by the drain. But people say, okay, they did a numerical simulation. They said it's not the case. Then we did the centrifuge test, and as you said, it's really almost a fully drained condition. It is very tiny and drained, but it's very limited.
But this is because your cyclic loading is, let's say, relatively slow.
Yes, in a way, yes. But another thing is, you can imagine in the field, it's more like a load-controlled condition. You have a wave and wind. But in the centrifuge, what we did is we applied quite large, and for this, we also did load control. But in this case, I show you the displacement control. So as you can see here, we really push the pile to a very large displacement at a very high speed. And so what we are doing here, even maybe is more faster than what's happening in the offshore. So even with this case, you don't expect that much pore pressure accumulation. So we think in the field it's even less maybe.
But I'm a bit puzzled because in reality the period of waves is something like what is it, like
10 seconds or something?
10 seconds, let's say, right?
Yeah.
So
I would not say that this is very slow. I mean, in reality, you also have 0.1 hertz more or less as a typical loading.
In reality.
Yeah, in reality, yeah.
But 0.01 hertz would be 10 hertz in the centrifuge, no?
We did the test at 50 G, so it's
yeah, this one is 100. Yes, yeah. So if we scale that should be 10 hertz, and we did only 1 hertz here.
Yeah, because it's difficult with actuators.
Yeah. So the good thing, as I mentioned, with that scaling law, we're still 10 times slower.
10 times slower than what the waves would be, right?
Yes. But we do it by displacement control. So the response of the load actually is even faster than that. So we are kind of compared to the field. Yeah. So that's the observation.
Also, one point is about the location of the pore pressure transducer. So these were, I believe, one radius away from the pile, and the next generation of measurements would be using the optical fibers, which are exactly installed at the skin of the pile. So over there, you can have a better observation of the pore pressure generation.
Yeah, that's a very good point, because we put the pore pressure sensor around 1 pile diameter away, but as you can imagine, when you're close to the pile, the soil deformed more, so there may be more response of pore pressure. But it's the centrifuge test. We didn't have time at that time to instrument the optical fiber. But we are going to do some numerical simulation to kind of quantify, okay, how much this will really affect the power response.
Mike?
Next one. The work you're doing with the blue pilings, is that in sand? And what is the main aim there of that study? Is it to optimize the loading duration or predict, what you're going to need to drive in different soil types?
Just one moment. Yeah. This is okay. Thank you, Mike. Yes, I think this one, our test it will be performed in sand, and the motivation for this is because the industry partner come up with a new hammer, which basically, instead of using a steel as the ram mass, what they are going to do is they put water inside this whole chamber. They hammer the pile, and which will generate completely different, like a false signal, as I show you here. Just one moment. Yeah, here, like if it's a steel, it's very the stiffness is very high, and there is bouncing back, so you can see the force with time is very sharp. Okay, this is a good one. So this black curve, and what the blue piling is generating is the energy is still comparable, but you can see the curve is much like wide, and and it will generate less noisy. And they try to see if it will get the same efficiency in terms of installation of pile, but generate less noise. And in the end, maybe that's a good direction to go for the offshore.
I think then obviously the following question is then what happens if you go into clay?
Yes, I think that will be a next topic. I guess we want to check, but in clay, I guess it really depends on what kind of clay in the offshore. If it's very soft clay, I think what we worried more is more like a pile running instead of really hammering the pile in. But if it's really stiff pile, yes, then it may be not that efficient. But we need to look into in the future, maybe. Yeah.
Because I think the pulse is a stat dynamic test. That's where the concept came from, which is what I did my PhD on in Rataflex. So clays is the fun bit. 3 times as much strength as static clay behavior at those kind of speeds. So will be fun.
Yeah. Thank you.
Indeed. One addition about the gray curve that we see here. We see that the integral of basically the energy between the 2 piles in this case is comparable. But the company IHC has foreseen to actually increase the energy by a factor of maybe 1 order of magnitude to basic, but still prolonging the pulse to about 200 milliseconds, so around maybe 20 times more than the impact hammer pulse.
So you maintain the pilot compression, which is the concept of standard pulse.
Exactly.
So Rob at IHC was the standard converter, so we just converted it to pilot.
Yeah, indeed. Yeah. Yes.
Yes.
So thank you very much for the because good presentation are also very motivational. So I want to ask your opinion about something, about the slide with the API method that we want to develop. So you said that most of the methods that they are there, they have some problems and they don't always can capture the response. And my question is, like the monopiles have the peculiarity that they are not slender piles, so we have L over D dimensions equal to 5 to 6, and with extremity threshold also equal to 3, which is much closer to the caissons. And so for caissons, it has been shown that you cannot capture the response if you don't include the rotational strings and you have only linear strings. And I understand that most of the methods they try to have only linear strings for simplicity, but it seems that without the rotational string you cannot capture. So I wanted to ask from your results if you have seen that as L over D is getting smaller, you have more difficulty in order to capture the response. This is my question.
Yes. Okay. I think this question can be answered by 2 points. First, the lateral soil reaction, basically this PY curves itself actually change with the power expect ratio. Or basically, if you check this design code API, it was actually proposed for a very, very small diameter slender pile, like maybe 50 years ago. And now we have very large diameter, very short pile. So the pile configuration completely changed, the mechanism changed. So even you don't consider the rotation spring or all the other components, the PYS model itself, it doesn't work. So people should improve the PY model first. But as a follow-up of your question, yes, when we get the PY right, when the pile becomes much shorter, it becomes kind of like caisson. Then you have the contribution more from the base, from the shaft friction. And at that moment, we need to add further like a new components like this distributed spring and base spring. And based on some like numerical simulation for the monopiles in sand, even with an expect ratio of like 5 or 3, the contribution from all the other components is still around like maybe 20 or maybe a little bit more if the pile is really very large or the embedded length is really short. So most times still the PY curves contribute most. But if in the future we really go to that large and that's short pile, we need to incorporate all the other components. And that's already as part of this project, I think, our design method called PISA. So that's the answer, yeah.
One last question, if there is. Yes.
What material model do you use for your numerical calculations?
Yes, for the MIDAS project, we are looking into the long-term behavior of the pile. So we really need to have a model that can capture the response of soil element after like hundreds of millions of cycles. So at UDEF, we already developed a model called Sunny Sand MS, which is based on the sand framework, but we incorporate the memory surface to capture the long-term behavior of the sand. I think it's already published. If you're interested, you can check that the paper. Yeah.
Yes, one very last question.
Just connected to these.
Yes, go ahead, please.
So basically, you said that you are going to incorporate the memory surface on the model. So my question is, have you observed in your experimental test a significant change in the response of the sand during the first cycles of loading? Because I imagine that if you need a memory surface, it's because you have seen an effect in the fabric of the soil.
Yes and no. Yeah, we can't really observe the change of the fabric because that's a different scale, of course. But from the response of the pile, you can clearly see the accumulation of the pile, like the rotation. You can see after many cycles, it keeps tilting, which means the soil must contract and fabric is changing. That's why you really need a model that can capture such many cycles. Yeah.
And what about in terms of stiffness? So
the stiffness also change, but depends on what kind of stiffness you are talking about. So if you look for each cycle, there is a loading stiffness. If you only focus an individual cycle, you will observe like at the beginning there will be some increase, but after certain cycles, the stiffness doesn't change that much. But you see still the rotation keeps accumulates. Yeah.
So in this 3D analysis, methodology.
Yeah.
And can you tell us about the time that it takes to calculate composite cycles?
I personally can't because that's a separate work. But I think for 100 cycles, it normally can take quite many hours, like 12 maybe or 1 day for 100 cycles. But we already implement this model in Plexis, which I think will take around 3 or 4 hours for 100 cycles simulation.
I have a question. You have an idea about what is the influence? So my question is, what is the influence of the installation effects on the long-term behavior of the monopipes?
Yes, that's a very good question. In our project we don't consider the installation effect. We do everything in wish in place or hijacking at 1G. But in the next step, we are planning to do some tests to really investigate that. And there is a separate project called the GDP, which investigate different installation methods like a jacking, vibrating, or hammering. Or there is also a torque combined with hammering, which is developed for that project. So you really look into how different installation methods will affect the later response of the monopile. There is some numerical work, I think, try to do it pure numerically. You can see if it's wish in place, you have more accumulation of the rotation. But if you simulate the impact driving, the rotation will decrease. So in that case, I would say like wish in place is kind of a conservative way to study, but we are going to look at that in more detail in the future. Yeah.
All right. Thank you very much, Juan.
Thank you.
It was very good discussion. And now we have